We've learned a little bit about the basics of how solar radiation is reflected, absorbed, re-emitted, and how the heat is moved around by molecules and particles. But when we consider these processes in our solar system, the sun's energy has very different behaviors with the different planets. So, for example, Venus has what we call a runaway greenhouse effect, and its temperatures sit above 400 degrees centigrade. And at the other extreme, we've got Mars with a very, very thin layer of atmosphere whose temperatures are minus 55 degrees centigrade. So what is it about the Goldilocks condition? Why is it that things are just perfect here on Earth? Well, firstly, from space, Earth looks very different. We are the blue planet. There are very few blue planets that we've come across so far in our rather limited exploration of space. We have an abundance of water. Water plays a really important role in the energetics of the Earth atmosphere system. Water molecules are attracted to each other by what's known as hydrogen bonds. And so when we want to break an ice lattice, we need to put extra energy in to break those hydrogen bonds or to stretch them. And especially when we go from a liquid to gas molecules in the atmosphere, we have to sever, we've got to break those hydrogen bonds, and that takes an enormous amount of energy. So water absorbs and releases energy in accordance with its state, and in doing so can alleviate some of the problems of a runaway energy system. The second thing that's really important about our atmosphere is its chemical composition. And we're mainly interested in the chemical composition of what we call the Homosphere. That's sort of the lower part of the atmosphere. The Homosphere is primarily made up of nitrogen and oxygen. This is very different to other planets. They tend to have atmospheres made up of hydrogen, sulfur, helium, and methane, which absorb a lot of energy. Nitrogen and oxygen are not really strong greenhouse gases. Mars is the only planet we know of that has traces of nitrogen and oxygen in our solar system. Now note that water vapor doesn't feature, and that's because those concentrations are averaged through the column of the atmosphere, and water vapor is only found really close to the surface of the Earth, and then again quite sporadically. So it's not quite on the table, but that doesn't mean to say it's not important. It is really important. The final thing that our atmosphere has that is relatively unique is that it's really deep, 170 kilometers deep. And if you have a look at this graph, you'll see that there's variations in temperature with height going up through the atmosphere. And we have the atmosphere is deep enough so that when we heat up the surface, the molecules warm, and then as they move away from the surface they cool, and so there's a decrease in temperature with height. And then when we get into the stratosphere, the temperatures, there's an area where it's reasonably constant, and then it increases and so forth and so on. And the other interesting thing about our atmosphere is that we've got a strong gravitational pull, and so most of the mass of the atmosphere is found very close to the surface, and pressure drops off very quickly. So this little layer that's in contact with the surface of the Earth contains most of the gases, but it's still deep enough that we can get gradients forming, and that's really important, as we'll learn in a few slides down the track. Our atmosphere is unique, lots of water, slightly different chemical composition, and deep.